This is the fourth video in our series on topology, and we're going to start this video by endowing the real plane with a certain natural topology, which we'll call the Euclidean topology. We'll do a couple of little examples and results of the Euclidean topology on R2 before moving to the notion of a basis of a topology. Okay, so in order to understand the Euclidean topology on R2, we need to recall the standard distance function. So that gives you the distance between 2 points in the plane. I think that should be pretty familiar. And then we need the notion of an open ball. And well, it's a pretty easy notion. So given a point A, B in R2 and a positive real number R, the open ball of radius R centered at AB will use this notation, so B sub R of AB. So it's going to be all points X and Y in R2 that are a distance less than R from AB. And let's observe real quick that I'm using these angle brackets for points in R2. And whenever we're working in a product, a Cartesian product of sets in topology, we'll choose the notation of using angle brackets for the ordered pairs or the ordered n-tuples in general. And that's because we've used maybe parentheses to be intervals in the real line. So we've got to make some sort of choice. Okay, so now we're ready for our definition. So we say that U, which is a subset of the plane, is open in the Euclidean topology if for all x, y in this set, there is a delta such that the ball centered at x, y of radius delta is totally contained in the set. And so here's a little picture of what's going on here. So we've got this set U in the plane, and perhaps since it's an open set, we should really have like maybe a dashed boundary, because as we'll see later, it won't include the boundary. But we'll leave it like this because that's a little harder to draw. Okay, so we've got this set U in the plane, and observe, we can take this point right here. Let's say this point is XY inside of U. And we can find a ball of radius delta centered at xy that's totally contained inside of U. Okay, so now let's start off by proving some results that are parallel to what we proved for the real line. And we're going to start with one of these open balls is in fact an open set itself. Okay, and so we'll take the open ball to be the ball of radius r centered at xy. Okay, so now let's perhaps suppose that angle bracket AB is inside of our ball of radius r centered at xy. Okay, so let's see if we can get a picture going of that right here. So let's say this is our point xy, and what we want is the ball of radius r with that center. Okay. So maybe this picture isn't perfect, but I think this picture is good enough for what we're going on here. Okay, so now let's take an arbitrary point inside of that ball, and let's recall that we should really be thinking about that boundary as being dashed. It does not include the boundary, but it's a little bit tricky to draw. So an arbitrary point will be this right here. And now let's observe that we've got something fairly similar to what we had in the case of the open interval. You can in fact think about this as just happening inside of an open interval on the line connecting those 2 points if you want. Okay, so let's maybe take a measurement first. So let's say that the distance from our point xy to our point AB, so let's get our point AB there, is exactly d. So we've got a distance of d there. And then let's say that the remaining part, or the distance from our point AB to the boundary here, is kind of pretty obviously r minus d. And observe that if we take a circle of radius r minus d, then it's pretty clearly going to be contained inside of our open ball. So that's going to be our motivation here. Okay, so let's set d equal to, well, like we have right here, the distance between those 2 points. So that's from xy to AB. And then let's also set delta to be equal to r minus d. So that's this thing right here. And then we'll make the following claim, which will finish this whole thing off. It'll finish showing that our open ball is in fact an open set, and that's going to be the ball centered at AB of radius delta is totally contained in our ball of radius r centered at x, y. Okay, and we'll prove that just simply with set containment. Okay, so let's take an arbitrary point inside of this ball right here, which maybe we could get a picture of that on the board. So that would be something like this. Okay, so that is our ball of radius delta. Okay, so let's take an arbitrary point inside of that ball. And what notation do we want to use? Well, I guess we're kind of running out of letters. Let's maybe take CD. Okay, so we're taking the point CD inside of our ball of radius delta from, or centered at AB. And now we want this CD to be inside of the larger ball, but in order to be inside of the larger ball, the distance between CD and XY can be at most R. So let's calculate that distance. So the distance from CD to XY, well, let's observe that that's going to be less than or equal to the distance from CD to AB plus the distance from AB to XY. And that's by something called the triangle inequality. But then we know that the distance from CD to AB is at most delta. And in fact, it's strictly less than delta. But then we defined the distance from AB to XY to be equal to D. So that means we've got this is equal to D. Okay, so anyway, this bit right here is strictly less than delta, and this bit right here is equal to D. But let's notice that delta is R minus D, so we can make that replacement. We have R minus D plus D, but that's equal to R. So looking way over here on the left, we've got the distance from CD to XY is strictly less than R. But that's exactly what we need for CD to be inside the ball of radius r centered at XY, which would complete this subset argument. Okay, so as one of your exercises, you'll show that an open rectangle is also an open set. But that being said, let's maybe start to look at the notion of a basis of a topology. So here's the notion of the basis for a topology. So let's say we've got a set X, and we've got a collection of subsets of X. And recall that we can say that as a subset of the power set. And we'll call this collection of subsets calligraphic B. And then this B is a basis for the topology T on X if it satisfies the following two conditions. So if you've got a set U in T, so in other words, U is an open set, and you've got a point X in U, then there's a set B in the collection calligraphic B such that X is an element of B, which is a subset of U. So kind of in other words is you can always get one of your basis sets inside of any open set, but you can also get any point you want inside of that basis set. Then next, if X is in the intersection of these two basis sets, then there's a third basis set where X is in B3, which is a subset of B1 intersect B2. So let's start by proving that if you take the collection of all open balls in R2, then that's a basis for the Euclidean topology on R2. Let's observe that the first condition is immediately satisfied by the definition of the Euclidean topology on R2. Now, let's look at the second condition. So let's take a point xy, which is in the intersection of two balls. So in other words, it's going to be inside of the ball of radius 1 centered at AB and the ball of radius 2 centered at, for instance, CD. So let's get a picture of that. Okay, so there's our point xy, which I have in yellow, and it's inside of both of these balls. And now we can really play the same game that we did before, just kind of two at a time. So let's set d1 equal to the distance from AB to xy. And then likewise, we'll set d2 equal to the distance from xy to CD. So let's get those written down. Okay, so there we've got that. And then let's also set delta 1 equal to R1 minus D1, and then delta 2 equal to R2 minus D2. And then finally, let's set delta equal to the minimum of delta 1 and delta 2. And so this is going to have the effect of creating a circle exactly small enough to fit in right here. And so let's note the following. So we know that the ball of radius delta centered at xy is going to be inside the ball of radius delta 1 centered at xy. And that's because delta is going to be less than or equal to delta 1 by this condition. But that's inside of the ball of radius 1 centered at AB by our construction, and that's actually exactly how we showed that open balls were open sets. And we likewise know that the ball of radius delta centered at xy is a subset of the ball of radius delta 2 centered at xy, because again, delta is going to be less than or equal to delta 2, which is inside of the ball of radius R2 centered at CD for the same kind of reason. And then furthermore, nominally, we know that xy is an element of both of these. Well, those two are the same set. Well, it's the center of those, and the center is always going to be an element of an open ball with a non-zero radius. But let's observe that since we've got these two subset relationships, that means that the ball of radius delta centered at xy is indeed a subset of the ball of radius R1 centered at AB intersected with the ball of radius R2 centered at CD. But that's exactly what we need for this second condition over here to be satisfied. And thus we indeed have a basis for our topology. Okay, so let's look at another example. Okay, so for our next example, let's take X to be any set, and then we'll take B to be the set of all singletons. So those are one element sets. And this is in fact a basis for the discrete topology on X. And so what was the discrete topology? Well, let's recall that the discrete topology was the topology where every set was an open set. So if we suppose U is a subset of X, and I'll put open here in parentheses, but because we're in the discrete topology, this is just any set. And then let's take X inside of U, and then we'll note the following, that X is inside of the singleton containing X, which is pretty clearly a subset of U because U contains X. And well, again, that's this condition over here, this first condition. Okay, well, next up, let's suppose that we have a point X, which is in the intersection of two basis sets. So let's say that it's in the intersection of the set containing x1 and the set containing x2. But immediately that tells us that the set containing x1 intersected the set containing x2 is non-empty because it contains an element. But the only way for an intersection of singletons to be non-empty is if each of the elements building those singletons are equal. So in other words, we've got x1 equals x2, but then that has to be equal to x because that's the point inside of those. But then, well, we've actually got it. Let's notice that X is inside of the singleton containing X, which is a subset of the intersection of X1 and X2. So it's kind of a silly argument here, but it is in fact what we need for this second condition to be satisfied. Okay, now let's look at a non-example. So for our next example, let's take X to be the 3-element set containing A, B, and C, and then we've got this collection of subsets. So the singleton A, the singleton C, and then the 2-element set A, B, and also the 2-element set B, C. And I'd like to argue that this is not the basis for a topology on X. And that's because we've got B is most definitely an element of the intersection of those two-element sets, but there's no set inside of B that's a subset of that intersection. But we can see that by the fact that the singleton is not an element of our collection, which would be a basis. Well, it's not a basis. So to finish it off, we see that there does not exist a set B inside of B such that we have B inside of B is a subset of the intersection of those 2-element sets. Because again, this capital B set would have to be the singleton, but the singleton is not in our collection. So now if you think back to the notion of a basis in a linear algebra class, you know that every element inside of a vector space can be built from the basis vectors. And so now we'd like to prove maybe a parallel result regarding a basis for a topology. And that result goes as follows. So let's let B be a basis for the topology T on a set X. Then for all open sets U of X, in other words, U being an element of T, U can be written as the union of elements from the basis. So this being written as the union of elements from a basis is like a vector being written as a linear combination of basis vectors, if you will. Okay. So now let's suppose we have an arbitrary open set inside of T. So in other words, T is inside of our collection of open sets T. Okay, so then for all X inside of U, we have some set Bx, which is an element of the basis, with X inside of Bx, which in turn is a subset of U. So that's from this first condition over here. And now we're going to make the following claim, which is going to essentially finish this whole thing off. And that is that U can be written as the union over all little u in U of this B sub U, where B sub U is a choice of one of these basis sets that contains the point U. And so we might be using the axiom of choice here, but we're not going to worry about that so much. Okay, so how can we prove this? Well, we'll prove it with double set containment. So let's start by proving that the right-hand set is a subset of the left-hand set. I think that's the simple one. So let's note for all U inside of U, we know our set BU is a subset of U. And again, that's by this line right here, by our choice. But if all of these are subsets of U, then that means that the union of all of them is also a subset of U. So again, that's what we need for this direction of containment. So now what about the other direction of containment? Well, we'll do that by tracing elements. So let's take an arbitrary element X inside of U, but that means that X is inside of B sub X, again, by our choice up here. But then B sub X is a subset over this big union because B sub X is one of the members of that union. But starting here and ending here is exactly what we need for U to be a subset of the union over all U in U of B sub U. But those two containments prove this right here. But that's exactly what we wanted to show. We've got our arbitrary open set is the union of our basis subsets here. So let's finish things off with another example. Okay, so for our last example, let's take C01 to be the set of all continuous functions from 0, 1, the unit interval, to the real numbers. And then let's set B of f epsilon to be the set of all functions g, so that when you take the integral from 0 to 1 of the absolute value of f minus g, you get something less than epsilon. Now, I'd like to point out that this integral from 0 to 1 of the absolute value of f minus g can be thought of some sort of measurement of the distance from a function g to a function f. And here, this is saying that the distance is less than epsilon. So what you can really think about this as is an open ball of radius epsilon centered at the function f. So although this looks kind of scary, if you think about it as an open ball in this more complicated situation, perhaps it's not as bad. And then what we'll show is that the collection of all of these open balls is in fact a basis for a topology on this set of all continuous functions. So we've got two things to show here, and that is that this script B satisfies these two conditions. So this first condition is pretty obvious, and that's because of the following. So if we've got f inside of C01, then let's observe that the integral from 0 to 1 of the absolute value of f minus f is equal to 0 because it's the integral of 0, but 0 is less than epsilon for all positive numbers epsilon. But what that tells us is that f is an element of bf epsilon for all epsilon bigger than 0. Well, if you think about this as the ball centered at f, this is kind of obvious. The function f is at the center of that ball, so it's going to be inside of every ball of radius anything centered at f. Okay, so anyway, like I said, there's not really much going on there. Okay, so now let's look at 2. So we need a point inside of an intersection of two of these things. So let's suppose that we've got G, which is inside of BF1 epsilon 1, intersected with BF2 epsilon 2. Okay, well, what does that tell us? That tells us the integral from 0 to 1 of the absolute value of F1 minus G is less than epsilon 1. And it tells us that the integral from 0 to 1 of the absolute value of f2 minus g is less than epsilon 2. But now we can add those and get the following. So let's notice we have epsilon 1 plus epsilon 2 is going to be bigger than the integral from 0 to 1 of the absolute value of f1 minus g plus the integral of the absolute value of f2 minus g. But then there's a rule involving, well, actually, it's simply the triangle inequality that lets us push those absolute values back together, but we might get something smaller. So this is all bigger than or equal to the integral from 0 to 1 of the absolute value of f1 plus f2 minus 2 times g. But we can divide this whole thing by 2, and we'll see that the integral from 0 to 1 of the absolute value of f1 plus f2 over 2 minus g is going to be less than epsilon 1 plus epsilon 2 over 2. Again, that's just taking this inequality right here, dividing the whole thing by 2, and then reordering things a little bit. But that tells us that our function g is inside of this b f1 plus f2 over 2, comma epsilon 1 plus epsilon 2 over 2. But then that's going to be a subset of b f1 epsilon 1 intersected with b f2 epsilon 2. Now we haven't exactly shown this containment right here, so I'll maybe leave that as a homework exercise. But we did show that G was inside of the first thing. Okay, so now speaking of homework exercises, I'm going to leave you with a couple of exercises. Okay, so here are 3 nice exercises. So the first one is to finish off that last example, so I've got it written right here. The second is to show that B1 and B2 are both bases for the Euclidean or standard topology on the real line. The first is simply a collection of open intervals A, B, where A and B are real numbers. And then the second one is almost the same, except now we take A, B to be rational numbers. So let's observe here that we've got parentheses, and that's because we're working inside of R, and these are intervals. They are not ordered pairs. Okay, so next up, let's show that this open rectangle, AB cross CD, is an open set of R2 in the Euclidean topology. So here's a picture of that open rectangle, and that's a good place to stop.